Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can implement shift left logic using Verilog, and then we are going to see how we can do the same in the VHDL programming. So first of all, this is a Verilog project, and here I have declared a module which is shift left logic, and it is an 8-bit module, and it has one output which is S and two inputs A and B, which are all of 8 bits, like you can see. Then I am assigning this A to S shifted by the value given in this variable. So this B we have defined actually of 8 bits like A, but we are going to use only 3 bits of this because A is of 8 bits. So in order to vary the bits or vary the value, we only need 3 bits of B. And if we are going to use all 7 bits of B, then we can have some complications. So that's why we are going to only use the 3 bits of B, although we have defined B as 8 bits. And this is the way we can define actually A and B once we are trying to design an ALU, and with the same inputs A and B we can say, due to our control logic, we can say, okay, if this is the case, then this A is going to be the plus of B, and if this is the situation control logic, then we can say A is going to get shifted by the value inside B. So that way we can define actually an ALU, and that's why I am using both A and B as 8 bits, but I am going to only use the 3 bits of B, and this is the way we should do. Like if we have A and B, for example, of 32 bits, then we can say we are going to only use 5 bits of B here. So same way we can vary for 64 and everything. So this is just the complete program. Now I am going to compile and run this program, and I am going to show you how this is going to behave. Now I am going to show you actually the test bench as well, which I am going to use for this program. Its module name is test bench, and then we are going to say S is wire, A and B are reg, the way we define in usually the test benches. And then we are going to call this module shift left logic, and we have to give a name here as well. And then we are going to say inside this initial block that as 0 time we can say set A and B equal to 0 0. We are going to start this loop, and then we are going to say increase A by 4 from here, and then we are going to say increase B by 1 using the same loop, and then we are going to say okay, wait for 10 nanoseconds. And after that, we are going to use these two values for A and B as well outside this for loop. And here we can also use 10 nanoseconds wait, and that's it. So let's compile this program. So now let's try to simulate this program and see how this is going to behave. Drag these three signals onto the wave window, and let's run the simulation, and let's expand this, and this is the way we are going to see our output. So this is our complete program, and we are seeing that if we are going to shift this A by 1, then we are going to see 4 becoming an 8. This is the way it happens, and same way all these values are going to get shifted. Now let's end the simulation, and I am going to show you another way of doing this shift left logic using this behavioral modeling. So we are going to skip this line and we are going to include these lines. So this is just the slicing and concatenation method. So instead of using these shift operators given by the Verilog language, we can use this slicing and concatenation as well. So here we are concatenating and slicing the bits. So for example, we are going to say that assign to S. So if B2 to 0, 3 bits of B, first 3 bits of B are 0, then we are going to say no need to shift, just assign 8 as it is. Then we are going to say okay, after that you can say if else. So we can say if B is equal to now 1, what is going to happen? We can say shift A from 6 to 0 to 7 to 1, and then at the 0 bit we can say add here 0. Same way we are going to add here 1 0, 2 0, 3 zeros, 4 zeros, 5 zeros, 6 zeros, 7 zeros, like this for all the cases. And after that we can say else make these all to the values of z, this s, right? So let's try to compile and run this program now. So our compile is successful now, and now let's try to simulate this. Go here, select simulate. Run simulation. Now expand, and we are going to see the same output here. Okay, and now I am going to show you just another way, a third way, using these assign continuous statements. So for example, instead of using this behavioral modeling, we want to use the structural modeling. So what we can do is, first of all, we can do behavioral modeling like this using Verilog on VHDL, and then we can convert that code to structural modeling. So in order to do structural modeling, I am going to show you how we can rearrange this or modify this Verilog code of behavioral modeling. So let's uncomment these lines, comment out these lines. So now this is actually, there are 3 assign statements here which we can use later to make this into a structural modeling or convert this into a structural model. Okay, now what we are doing here, we are just defining 3 variables which are of wire type because we are going to use the assign. So S1 and S2, we are going to define 2 variables. Now what we are doing is we are saying that this S1 actually represents shift by 1. Okay, so what we are going to say, we are going to say okay, check B 0 bit, just like the way we are going to do here. We are going to say okay, if B0 is equal to 0, just assign A to S1 like here. Then we are going to say now if B0 is equal to 1, just like in this case, we are going to say now shift this and add 0 to it from the right side so that it can shift towards the left side. That's why we are placing a 0 from this side and we are shifting A by this. So this is from 0 to 7, at the 0 bit, 0 is here, and all the other 7 bits, first 7 bits are going to transfer from 7 to 1 bit of this whole. Okay, and now we are going to say actually shift by 2. Okay, from here, and we are going to say okay, let's check now the B1 bit, like these bits 1 1, these 2 bits, and we are going to say what is the condition of middle bit B1 bit. If it is going to be 1, then shift this signal by 2 zeros, so add 2 zeros from this side and shift all the other S from 0 to 5 to this position. Okay, this is the way we do the slicing and concatenation using Verilog. And now we are going to say, what about the case if B, the number 2 bit is going to be a 1. So from here we are going to see B number 2 bit is going to be 1 1 1 1 1. Okay, so we can say now if the B's 2 bit is, which is going to be the third bit actually of this P code which we are getting, we are going to say if this is 1, then we are going to say add 4 zeros from here. Okay, so just like this here, it is going to be become 1 for the first time, and we are adding here 4 zeros, and we are going to say add 4 zeros from this side, and this is the way it is going to check. So to which variable we are adding these 4 zeros? To this S2, not to A. So this is the way gradually we are going to shift all the bits just like this. So in the case of A, we are adding 0 from here, then we are going to say this is going to become now S. This first shift has happened. Then we are going to say using this S, now we are going to check for the this, once this second bit is going to be 1. So we are going to use it like this, add 2 zeros, like here we are adding, and then whatever result we are going to get using this S2, now we are going to add these 4 bits. So this is the way we can do all these from 0 to 7 zeros we can actually change. So in order to get this theory, you can search online as well, but this is the way we usually design a shift left logic like this. So just these 3 code lines, and later using these 3 code lines and muxes, we can make a structural model of shift left logic as well. So this is just the complete program. I can show you by saving it and running this program as well. So let's compile this program again. Testbench simulation. So drag these 3 ports here. Let's run the simulation. So we are going to see the same results here. So this is pretty much all about shift left logic in Verilog. So now let's go over to the VHDL project and let's see how we can do the same thing using VHDL language. Close this project and open the next project. So now let's go to the VHDL files. This is our VHDL design file in which we are using this entity, and we are going to say entity is shift left logic, and it is going to be also of 8 bit. So 8 bit S output, and A and B are 8 bit inputs. And after that we are going to say the architecture of shift left logic is, so we are going to use this SLL from this library, IEEE STD logic 1164.all has this SLL. But remember that in order to use this, we have to convert this file by going into its properties to VIDL 8. Right click here, go to properties, use this VIDL this 2008, not the default option 2002. Otherwise, this SLL is not going to work in your program. So remember this thing. And what we are doing here is we are just saying that pick up A 8 bits, shift left logic, use this, and we are going to see that how many bits are going to get shifted through this B, and B is again going to be from 2 down to 0, only 3 bits, because our A is of 8 bits. If A is going to be 32 bits, this is going to be of only 5 bits. 2 raised to the power 5 is 32, and then we are going to say 4 down to 0 instead of 2 down to 0. Instead of 2 down to 0, remember this. So this is just our complete program and this architecture here. So now I am going to show you its test bench as well. So this is the test bench file, and on the similar pattern we have defined the test bench in VHDL. So this is the test bench entity's name, and after that in the architecture we are going to call this component the same entity which we have defined to design our shift left logic, and we are going to use that as a component. It has again these 3 ports, and after that we are going to use this signal to connect those ports to this module which we are calling here shift left logic of our main design. And here we are going to use this port map to map all those inputs and the outputs, so S, A and B, using the positioning. And after that we are going to say start the process, and inside this process block we are going to say at first make these A and B inputs equal to 0 0, and wait for 10 nanoseconds, start this for loop, and we are going to again say increase B by 1, increase A value by 4, X value, and then wait for 10 nanoseconds and this loop. Then we are going to say again make A is equal to this, B is equal to this, so that we can test all the cases, then wait again, and then wait so that this process block doesn't run forever. So this is our complete program of test bench. So now let's try to simulate this program as well. Go here, right click, press simulate. So we are going to see the same output like this for the shift left logic. Now let's end this simulation, and I am going to show you some more ways as well to do the same thing in VIDL, so that according to your needs, the way you are going to design, do these simulations, synthesis, gate level synthesis, everything, so that you can work like that. So let's go to this VIDL file, skip out this line and include these lines. So this time we are going to use the shift left function which is given in this library, numeric std.all. So this library actually gives us shift left unsigned and 2 integer, which we are going to use in this. We are going to use the 2 integer here, unsigned here, from the same library shift left here, in order to shift left according to the value which is given by B, right? So this is just another way. So now let's again go here, save this, compile this, run this test bench according to this new code. run, and we are going to see the same output in which we are going to get the S shifted by these values 0, 1, 2, 3, 4, and this is going to be our input and this is going to be our output according to that. And the simulation, and now I am going to show you just another way of shifting the things in VHDL so that you know all the ways using VHDL as well to shift left according to your needs. Keep out these lines. So in VHDL there are actually 4 ways. In Verilog there were actually 3 ways. So now we are going to see the third way. So this is also behavioral modeling. Let's compile this. So here we are also using the same thing, like we can say that check B first 3 bits, and if those are all zeros, make S equal to A, don't shift. And then we can say, okay, if B first 3 bits have this value, we are using else here. So then shift by only one and add 0 here to the least significant bit. Then we are going to say if B's value is this 2, add 2 zeros and shift, and then we are going to go until is 7 for all the cases, just like we did in Verilog as well. So I can show you the simulation output for this case as well. So we are going to see actually the same outputs. Let's try now the fourth way. So in some cases VADL is better, in some cases Verilog is better. For this case actually we see more options as far as VADL is concerned, but in some other cases we are going to see there are many options in Verilog but not much in VADL. So it depends. So this is actually the again those 3 lines of code which we can use to change our behavioral model into a structural model. The way we are going to design that structural model, we can modify our behavioral code like this first of all, and then we can use the muxes over these 3 lines. So we are going to define 3 signals which are going to give us shifted values towards the left gradually. So for the first shift, we are going to use this S1 which represents actually shift by 1, and we are going to say, okay, check this B0 value just like here. If B's least significant bit is 0, then assign A is else, or otherwise if B0 is equal to 1, then shift it by 1 and add 0 here. This is actually this one. So add 0 here like this. And then we are going to say now this gets shifted by 1. Now what should be the case? Now check if b this second bit b1 is going to be 1 or 0. So if it is 0, just like here for the first 2 cases, we are going to say okay, if s1 as it is to s2, or otherwise we are going to say if B1 is going to be 1, just like for these two cases, 1, 1. Then we are going to say, okay, do the concatenation, and then we are going to add of this S1. So we are going to concatenate, and we are going to say from 5 down to 0, these are going to go from 7 down to 2 actually. And then we are going to say from the left side add these two zeros so that we can do the shift left logic. And then we are going to use this S2 now. Using those second shift, we are going to say now check for the fourth shift, four shifts. So here we are going to end actually on the four shift. If our this A and B are going to be 32 bits, then we have to add two or three lines again as well, like for the first shift, two shifts, four shifts, and then eight shifts, and then 16 shifts. We are going to add two more lines. But in this case, we only stop here at the fourth shift. Going to use now this two shifts, and then we are going to say now check this B2, the third bit, if it is going to be 1 for these all four cases, later four cases. When this bit is going to become 1, we are going to say okay, now use this S2 and put this S2 as it is to output if B2 is going to be 0, just like for all these first four cases. But if it is going to be 1, then we are going to say concatenate and add here. So we are going to say pick from S3 down to 0 and place those here and add four zeros from the right side to shift towards the left side. So this is going to be our output. So this is the way actually we usually design our code to convert it into a structural implementation to test on our designs according to our needs. So we are going to see the same output again, save it, compile design, simulate. So now let's drag the three signals. Select these three signals and drag those to this wave window and run this program. So we are going to see the same output on this simulation, and you can test this on your end as well. So this is pretty much the behavioral design of our shift left logic using this VHDL code. Now there were four ways to do this using behavioral modeling in VHDL, and there were three ways using the Verilog language to do this behavioral modeling of shift left logic. So thank you guys. I hope you guys have enjoyed this video. Have fun.